Hello everyone, welcome back. So, we will take some more examples today, and one of the application where we want to transfer one of rotation and is very frequently used. So, either is we call it rotation, and if we consider that constraint and where we are assuming that the bodies are rigid, infinitely rigid. So, it means rotation, it means we can also transfer the torque. So, very common application where we want to rotate one component with respect to the other, and when we are looking for applications where we had to point devices, we have to rotate precisely, and sometimes these numbers can be very small, maybe of the order of arc seconds. And what we realize that if we are looking at those numbers, the friction and any kind of rolling contact may not be good. So, in that case the coupling has to be proper, and we can use a constant approach, the exact constant design approach, and then we will see that we can eliminate friction related problems, the virtual backlash, the hysteresis part. So, for instance, this is the input and this is the output, and what we observed here, there is an offset here. So, in many applications when we are like transferring rotational motion or the want to transfer the torque to the other side through shafts, we use coupling. And what is important to understand is what is the role of coupling, and many times we make a mistake of using rigid couplings, and then we will face a lot of problems, because if it is a rigid coupling, then the two shafts, they have to be aligned perfectly, the offset alignment, and that has to be taken care. And if we really want to get rid of those requirements, then we have to understand the constraint requirement of a coupling. So, for instance, here what is desired is, if you are rotating, the other side, the output side should also rotate by the same amount or in a predictable way, in a deterministic way. So, that is the only constraint we want to have with respect to each other, the two shafts. So, and that is why calling it transferring one DOF a rotation, right. So, transferring one DOF means the two bodies are constrained, and they are constrained in rotation only. So, all other 5 DOFs should be free. So, we have 5 degrees of freedom in this case, and this has to be coupled. So, offset is one, other is like misalignments also. So, we do not want to have any kind of misalignment. So, suppose if we have two shafts here, so I have exaggerated bearings here. And here we have the black box, which is called coupling, and the coupling should provide that degrees of freedom. So, what we see here is actually flexible coupling, and in many of the rugged applications, heavy applications, there we might not be looking at precision, and then we can simply get off some elastomers or rubbers and some kind of tubings where it can flex easily, and then we can clamp it and it works. So, it does all of them, and the rotational constraint is there, but yes, because it is a flexible in that direction. So, it is a very difficult to get that precision in this case. So, if we try to look at it closely and if we want to constrain the rotation part, what we have discussed earlier, that the two shafts there, and okay, it might be overlapping or there might be some offset and misalignment. So, it will be the second can be slightly off with respect to the input and output. So, there is some offset, and yes, if it is a misaligned, so it is a changing as well. What is important to understand that yes, we want to have this constraint, and what we also realize that if we constrain, we provide the constraint away from the axis of rotation, and the constraint is not passing through the axis of rotation, then it will provide that rotational constraint, and it means one constraint away from the axis of rotation is sufficient to provide that constraint, rotational constraint, and that is what we see here. So, we can extend one arm and connect to one member, and another one connect to the other side, and we can just use a pin, connect it, and it is more than sufficient, and that is what we see here. So, one flange, so what you can see here, and so 1 and 2. So, you can see that the shaft here, and one flange we have connected, on the other side we have connected another one. So, and they are connected through this wire flexure, or just we can say a linear constraint. And if you try to see, if you try to rotate one depending on the direction, either it will be in compression or in tension. But what we realize that is a sufficient, and if there is any eccentricity, offset, whatever we have here because of the misalignment or even the axis, there can be an offset. So, because of those things, if there is any eccentricity in the shafts at the point of location where we put the arms, what we realize that since it is an articulated link, so it can move, it can shift a little bit and can accommodate that, and as it moves, even if though it is varying, the position can change. So, articulated link is good enough. Later we can replace it with the wire flexures, and if you really want to test whether the constraints, this kind of constraint can work, we can put in an antagonistic way, and we can simply put a kind of thread or flexible cable also, because in that case one of them will be always in tension and it will give that required rotational constraint. So, this is one exercise, and if you have access to 3D printing or some other ways, you can machine it, and very simple, just insert a 1 millimeter diameter wire or even thinner, and get this one and kind of extension, arm extension. You can provide the offset or misalignment between the two shafts by shifting the bearing locations, and you can test yourself that it's a very good solution. And once you realize that, what you realize that is so cost effective, you do not have to look for very complicated coupling, or even the offset and the misalignment requirement can be alleviated. We can get rid of all those requirements, and we can relax those tolerance or assembly requirements altogether. So, if we extend and there is a need because it is not symmetric, it is slightly offset. So, what happens if you are looking for high speed applications? It may not be very good because some eccentricity will always give rise to a lot of dynamic loading, and then we will have a lot of vibration. So, if you want to address that, then we are looking for symmetric solutions, and although it is what you see in this case. So, although it is over constrained design, but it is symmetric and flexible. So, it can be accommodated easily. So, what you see here is you have a inner piece 1 which is connected to this side, and then you have the outer one. So, it is more like 2 disc. So, you have the smaller one and then you have the bigger one. So, it is like a disc with the overlapping flanges, and then you connect them using these kind of wires. What you see here is you only see the bare part, but yes, it is actually inserted here and clamped. And what is interesting and what is important to remember is if we extend and drop a perpendicular, we should always find this, call it R. So, it should away, it should not pass through the center. Moment it passes through the axis of rotation, we do not get that coupling effect or the required constraint. Although after some time it can rotate, but then since it is not constraining, and after some rotation only it can provide that torsional moment, and then you can move, but the precise location is not possible. So, if you have this, it has to be any axis. So, it can be from here to here, but what is important is when we drop the perpendicular, there should be always an offset, it should be away, and because that is what provides you the required torsion to move it, and the stiffness of this member is important in that case. So, another embodiment, and what you can also see that is equivalent to universal joint. So, it can flex easily, and it can also, so you can check yourself, you can define the axis, different axis x, y and z, and even you can think of the rotation, and you can check yourself that how we are getting one constraint and 5 degrees of freedom in this case. So, very good example, and flexible coupling. So, since it's just a manifestation of the earlier concept, and then we replace the articulated link with the flexible member, which is wire flexion in this case. So, moving on, what we realized that if we use it 2 times, and then what we did, we just extended. So, suppose you have one coupling here, can put another one. So, it is a universal joint. So, you have 2 universal joints. And there are many such applications where we need that. So, we have input and the output, they have to be parallel, but then in between there should be an offset, and We want some flexibility, and so therefore, it is very important to have that. And what we realize that this simple mechanism can solve the problem. So, from the other side, that is what you see. Of course, because of the offset is there will be overlapping disk, what you see, and even the shaft location, it will be changed little bit. But yes, what is important is just 2 thin bars we can use, and we can create very nice mechanism. So, using that concept and one constraint away from the center, now we can have many solutions. So, traditionally any coupling, if you want to have, whether it is a heavy application or whether we want to transfer a large torque, and using a rotary motor. So, we have in and out, and this is the traditional Oldham coupling we are talking about. So, you can see the number of parts. So, the counts, there are many components, many parts here. There are many surfaces sliding in and out, and the intermediate part, this is the intermediate part which is doing all the kind of shifting and moving in x and y directions, and try to compensate if there is any offset or any misalignment, and that is how we get rid of or we can address the offset between the two shafts. Because of the sliding surfaces, this has to be lubricated very often, and with the wear and tear we may have to replace it. If we understand the constraint and flexible constraint and applying a linear constraint, so what we can see here, there are 4 of them, just flexible part. So, 1 on this side, 2, 3 and 4, and it is a symmetric design. Again, it is a, one can say it is a over constraint, but it is a symmetric and flexible. So, it will readjust, and the angle, the rotation what we want to transfer to the other side, or even the load is it will not provide any kind of moment transfer or displacement transfer from one side to the other, except the rotation which is desired. So, phi. So, this is the constraint what we want, and each one of them will provide that. What do you also understand that the two sides, so like if you, I just number it 1, 2, 3 and 4. So, what you can see is opposite ends here. So, connected to the input shaft. So, suppose this little pinkish one is the input shaft, is connected to 2 and 4. You can see it is bolted here, and then you have, so one side connected to this thing, and then 1 and 3, 1 and 3, and they are connected from the other side. So, you turn, this will also get turned. So, the coupling here is just a thin plate. You just take a very thin plate and make this a structure. So, you just remove the material. Yeah, you can, if you really want to have a very rough one, you can even use saw and just make those slits. And what is important is this functional part in the center what you have. So, beam like a structure. So, here is a, suppose you can simply take a thin disc and maybe very small thickness T, even a disc of thickness 0.5 millimeter should be sufficient enough to provide that constraint. So, So, again very good example, and what it says, torsionally stiff coupling based on elastic elements and equivalent to all lamp coupling. So, what we realize that even a thin disc, and if we cut in this fashion and attach to the two ends, so any kind of motion between the two shafts, the misalignments, offset, all can be addressed with that very simple disc with that kind of features. And since there are no sliding friction involved, so the lubrication, wear and tear, there is no question. So, if we design it using the concept what we study in design of machine elements, and if we take care of suppose if it is a dynamic application, the fatigue and all those things, if we take care, what we realize that we do not even need to remove or service these parts. Moreover, if we are looking for some application in vacuum or in a space and we need to couple, we can easily get rid of any traditional old lamp kind of coupling and we can go for flexible coupling. That is the biggest advantage we can have. So, there are similar kind of couplings and is called Koster coupling after the name of Professor Koster from Netherlands. And most of the design what you see here, they are originated from Philips Eindhoven, Netherlands. And yes, originally all the materials, all this literature was available in Dutch only, but Professor Summers has translated it in English, and we are referring to his book, Design of Precision Mechanisms, and you can refer to. So, many of these materials are from Philips, and definitely ASML is also a spin-off of Philips. So, all these elements, if you look at those machines, they are everywhere in most of the machines. So, any precision machine, if you look at the flexure elements, the degrees of freedom, this kind of couplings will be embedded. And after this course, I think you will be able to understand and you will be able to appreciate why these features, these small holes, these small slits and cuts are provided, and how this flexibility provides you a good solution and good way to overcome any kind of to address the problem related with over constraints, and you can get a very cost effective solutions using these methods. So, yeah, it is same what we discussed. So, you have the disk and then you have these features what you see here. And you can see it is just a very thin section here and then clamped like this, and then you get the desired effect. One very important thing to also note down is this feature, how to clamp it. And usually one of the means if you really care about precision, you do not lock the shaft radially, you always try to clamp it. So, what you see here is the shaft, and then you have this element. What you see here is a small hole and then cut here, and then slightly bigger one here, and then again a gap here. And I think we should always remember this thing. So, with the clearance we can slide it very easily. What is important to note is we can have a threaded hole here and here clearance hole, and then we can put the screw here, tighten it. So, what we realize, moment we tighten it, this gets closes, and this end, this part is very important because the thin section will allow that bending to happen. So, these two parts it just bends, and as you tighten it will just clamp this surface. So, it get tightened, and this way you will not damage the surface of the shaft. Many times it is a very important and very easy to remove also, because it is still within the elastic limit. So, if we take it out, then again it will spring back, and then you will have the proper clearance and you can remove it. So, that way you do not damage it. So, always remember, I think this is one of the design elements I think we should remember. We should never do this kind of things. So, many times we just drill a hole, tap hole, and then try to lock it, but it damages the surface and it is not reusable. It is a no. If you are doing this course, it is a strictly no, and we should not never use that kind of locking mechanism to couple or lock the two elements in rotation. So, this is the detailed one, and another embodiment I would say. Embodiment design of the same concept, and so this is what I was referring to, this element, and so the intermediate section. So, this is the functional member. So, sometimes in the exam and in discussions, in technical discussions, we also ask in the entire thing which one is the functional element. So, out of this big thing, what you realize, that tiny part is the functional element, which provides you the required constraints, but at the same time it also provides that flexibility, and that is how you release the 5 DOF, which if we constrain, then it will be over constrained, and then we may have to give some tight tolerances in some of the things. So, be aware of that. What we did here is, now I think earlier we discussed, and when we cover fracture mechanisms, this is one kind of flexure we will be using very often in our designs, and mainly because it is easy to use and it gives a very good way to constrain one translation. So, if we just do this, what we learn is this is the constraint direction. So, if we replace this one with this, so stick now replace with the folded leaf spring or folded sheet flexures. So, in short, what I refer to is FSF, folded sheet flexure. Yes. And now we replace all these line constraint with the folded sheet flexure, and I think one should be able to appreciate that part. Just look at it, this section, and what you realize that you just take a thin sheet and cut this way, and you should be able to see shortly why that is required. And there is this one. So, what happens if you fold, if you only fold till here. So, then alternately you bend it 2 inside and 2 on the other side, left and right configuration. So, what you see here. So, one side and the other side. So, now is clamped to the 2 disc. What is important to note is this overhang, which is because of this thing. If you clamp it tightly, then you will have an issue. It will happen only if there is this fold structure. So, you are clamping here, you are bolting here, but this overhang is there. So, which is one of the side, and this one is this part which you get because of this cut, undercut you have. So, that section will provide you. So, one part and 2 part. So, you get that fold structure, and this line and this one is the your linear constraint, and since it is away from the axis of rotation, you will get that rotational constraint. So, 4 of them. Again, if you are looking for any mass scale production, what you realize that is a very cost effective solutions. You do not need many parts, just one sheet metal and stamp it, cut it, bend it, that is it, and you get a very good coupling. And at the same time it will be torsionally stiff, because you can imagine if there is a sheet flexure, and along that line later we will do the mathematics and try to get the stiffness values. So, it is very high, and again it is a very good solutions, and it is a flexible. So, again the maintenance, wear, tear, lubrication, all those things can be easily eliminated, and therefore can be easily used in a very rugged environment as well. So, even for solar applications. So, suppose if you want to design solar farms and want to articulate the joints and run the entire farm with the few motors only, but what about the coupling? You may need to couple each units. So, whether you are going for all them kind of coupling or those kind of. So, if you are not aware of these things, you may be going for those kind of solutions. But if you are aware, you know that a simple sheet flexures can work, and yeah, you can make out of sheet metals and just bend it in this way and attach it, and you can get a very good solution. So, this is just a CAD model, and this is what you see. So, for better illustration, and this is what I was talking about, the overhang. So, that we get the real flexure, sheet flexures. And on the other side you have the other piece. So, if we keep extending the concept, we can have many solutions, and what we also realize that again we want to have the want to transfer the motion, the rotational motion, and we extend, what we realize, any kind of disc. So, this is now call it sheet flexures or leaf spring. Or a sheet. If we take, again we can talk about the compliance. So, 3 compliance and 3 constraints, and similarly we can have other side also. But if we connect the 2, so we want to have an offset, but is connected through a torsionally stiff member. That is the requirement. So, that is what you transmit. So, moment you want to transfer the displacement, whether it is a rotary or So, you need a one-to-one correspondence and the constraint is required. So, how you are getting is because of this rigid coupling. Again, this solution is very eccentric, I would say. So, for a static application it might be okay, but for dynamic application it has to be replaced with the symmetric design. And if you look at it closely, what happens if you expand the inner part? So, initially is to one side, now you increase and then envelop the entire thing. So, this is what you get. So, a drum, and again you connect these two sides. So, now call it a diaphragm or whatever you can call it. So, two sides provide the notches, so it can flex, but what you realize that if you want to rotate, that can be easily transferred. So, because that constraint is there, and so it's a symmetric, so you can use for high rotational velocities also. So, again it's a clever design and embodiment of the similar concept. So, if we want to build any kind of design or mechanism with certain degrees of freedom, we can use the concept, the constraint concept. But we also realize that many times if we are aware of these solutions and how to apply the constraints to get rid of certain degrees of freedom, we can also address problems where means the boundary condition, because of the other space requirements, we face many challenges. So, for instance, if we look at this example, what is saying constraining axial displacement without using material at the center line. So, you can always think of, suppose I have to constrain this one axially. So, one can always say I can provide something at the bottom and can constrain along this line, but the application is such that I can't have anything here, but it can move around little bit, can twist, rotate, but I need to have a constraint along the axial direction. So, how to do that? So, this is one of the approach. I think we can also use it. So, starting from the base. So, base you have all the 6 constraints here. So, because these are rigidly fixed to the machine frame or to any base, if we have, we can constrain it. Go to the, so it's a A. Now, moving to H, the intermediate member. What we realize now, we use 2 linear constraints, 3 linear constraints there is on the other side. And if we have this kind of a structure with the three linear constraints, what we get is it constrained in a plane. So, it can only move in a plane. So, what we will have here is, so this is the frame we are talking about, x, y, z. So, z will be constrained because it cannot go out of the plane, that plane defined by h, and the 2 out of plane rotations. So, these 3 are still constrained. What you now achieved by combining or constraining this platform H with the 3 wire flexure, you get rid of x motion, y motion, and the theta rotation. Now, if you go to the next stage and use another 3, but now this time is incline, and if you extend, they will meet at this point M. What happened in this case with respect to H? It only constrains the z direction. Now, you can have at this point, it can have those rotations. So, what you realize that the z constraint is moving from base A to the shaft, and that's how you can have this constraint, Z constraint, but all other motions is possible. So, but yes, you can see at the bottom. So, you are holding it at a very far away place, and at the bottom you do not need any material along that plane. So, if you have such application, you can always use this example and can design things around it. The next is, how about like providing a radial constraint, I would say, or suppose if you want to align two shafts or two components and they should be aligned along certain axis, how to design that. So, the term used here is self-centering driver. So, we are using the concept. Many times what we see is we use a lot of splines. So, not 1, 2, 3, but many of them, and we assume or we just believe that it will be self-centered. But if we look at it closely, what we realize that it's a random, and how many will be in contact. There are many surfaces, but at a time how many will really come in contact. So, for instance, if you are talking about the flat surfaces and want to put any block here, although we can call it flat. So, on top of a table and want to put a flat object, we can always say, oh, there are many points. But if we look at it closely, and what we realize that wherever it's touching, actually those are the highest points on the two surfaces, and they first come in contact. Yes, locally they deform and we do not see any gaps, but if we know, means there can be at a time only 3 contacts. Similarly, in this, so this is what we say here. In case of radial thing, and suppose things are rotating, here also what we realize that 3 is the number, 3 contacts, and they will define the position. And if there are many here, many teeth, splines here, only 3 will, whichever comes in contact first, they will define. Although, okay, we try to leverage on, okay, there will be wear and tear, and the other 3 will come in contact, and then there will be uniform wear and tear. But after some time, then it may not work, and then we have to replace with the new splines, and there can be a lot of play. What we realize that if we use the concept of exact constraint design, these 3 contacts can be predefined, and we have to worry about only those 3 contacts. And that is why we say that if we follow exact constraint design principles, we can determine the position of the 2 objects precisely. So now if you just talk about the 3 surfaces here, 3 splines only, and this is the constraint provided, right. So, again it is a constraint, linear constraint away from the center, and yeah, there is also a concept of thermal center. So, what you realize that when this object, if there is any differential change in dimension, so either contraction or expansion, thermal expansion, this thing will simply slide. So, that is why you see the rollers here. So, it will not constrain, it will not provide any kind of over constraint. So, it can easily slide, but what is important is at this point will be invariant. So, moment we have this, actually it gets centered automatically. So, suppose if we have to these two members 1 and 2, and if we are able to define these three contacts, actually it gets centered. So, shaft remains centered in relation to other, and every point of contact has equal load. Of course, it depends on how we apply the preloading, but yeah, if it's a moment, torsional moment we apply, right, then since it's a symmetric design, it will be equal at each and every contact point. Very difficult to visualize, but if we do the math or if we just try ourselves, we will see that it works, and we do not have to like locate it radially, because many times what we do, if we have to do such things, we do this kind of adjustment, right. And maybe some thread here. So, we adjust and then try to locate the center part. Of course, it damages the surface, which is not good, and yeah, means all the three it has to be adjusted, and then we may need some external means to know where exactly it is. So, of course, we are not going for that. Instead, we go for this solution, and what we realize that actually it's a self-centering driver. It drives it to the center, and it depends on the how we create these surfaces, how they are aligned. So, we have one example here, and what you see here is I have just 3D printed the part, and yes, a lot of clearance what you can see between the two. But moment I apply or give a nesting force, so in this case just the clockwise. So, to the red object, if you just give this torsion moment to the red object, so it comes in contact at these 3 points. A moment you establish these 3 contacts, actually it will always go to the center. So, you can easily see that although it's very wobbly, but moment I apply the torsional load, it will always go back to the same location. So, you can see it here also. And to lock it, you can have different means. So, I just 3D printed another one and it's locked, and you can see that is centered. So, I can push it and take it out. It's not very clear here, but I have a video, so that you can see very clearly. So, now the center part now placed to the base, and then you realize that a lot of gap, and the center, yeah, means it's moving all over. But moment you apply that clockwise moment and establish the 3 contacts, you see that it's going to the center. So, this is just a locking mechanism or a mechanism to provide that nesting force. So, just click it and lock it, and it moved to the center. So, you can see that it's aligned. So, very easy to make. If you have access to 3D printer, you can use it and can see it yourself. So, again, if you understand and you know the principles behind it, one should be able to design such devices and can use for different applications. So, you do not have to make conformal surfaces, very tight tolerances to bring something to the center or align the two parts, but just with this kind of constraints provided, you can relax all the requirement and still you can get a very good alignment, and the thing can fall in the center. So, we will have many such examples, and so some with the contacts and some with the equivalent flexure mechanisms, compliant mechanisms. So, when we talk about different compliant mechanisms, we will revisit these concepts, and we will also try to see how it is extended to flexible mechanisms or compliant mechanisms, and how these features or these properties we can use to better design things for higher precision and for very precision applications. So, these are the references, and for this part most of the contents are from this book, Design Principles for Precision Mechanism by Professor Soomers, and as I mentioned is mainly from Netherlands, from Philips and ASML. So, you see a lot of designs, and as again as Cocoon, Elements of Mechanical Design and Blending, very good books, and you can always refer to the books, and if you have any doubt, please pose those problems and ask those questions. We should be able to answer and discuss those problems one by one in coming lectures. Thank you.